Welcome back, everyone. My name is Anne-Kathrin, and I'm currently a lecturer at ETH. I will host this first tutorial of the Photonics Online Meetup with our wonderful speaker, Dr. Sebastian. First, let me introduce him real brief. Sebastian was born in India. He received his PhD in electrical engineering from Iowa State University in the US. And after 2 years as postdoc, Dr. Sebastian became a research staff member at IBM Research here in Switzerland in 2006. There, he currently manages the research efforts on in-memory computing. As a master inventor, was named principal and distinguished research staff member. Dr. Sebastian was also awarded numerous grants and awards such as an ERC Consolidator and Proof of Concept grant, or the Ovchinsky Lectureship Award for his contributions to phase change materials for cognitive computing. And just a few days ago, his and his collaborators' work on how light and in-memory computing can help AI to achieve ultra-low latency was published in Nature. So now we're very much looking forward to his talk on brain-inspired computing. And after his presentation, we will have about 15 minutes for questions. So please write in the chat what you would like to know or discuss, and no worries, every question is welcome. So thank you, Abu, for agreeing to give this tutorial. We're very excited to have you, and the virtual stage is yours.
I hope you can see my screen, right? Well, yeah, so I would like to thank the organizers for this kind invitation and for Anne-Kathrin for all the nice words she said about me. It is indeed an honor to be part of this amazing online webinar. I mean, it was really extraordinary to see the enthusiasm on social media. Now, given the broad spectrum of audience that I suspect would be tuning in, I've decided to give a rather high-level overview of the field of brain-inspired computing. So this is how I'd like to structure the tutorial. So first, I would like to agree on what we mean by brain-inspired computing. Then we will look briefly at the origins of artificial neural networks. Then how artificial neural networks came of age due to the innovations in information technology. And then we will invest quite some time on new computing substrates for artificial neural networks. And subsequently, I would like to give at least a small glimpse of some algorithmic developments that go beyond traditional artificial neural networks. And then finally, I'll give an outlook and summary. So now if you look at the human brain, as you know, it's one of the most intricate objects in our universe, right? It weighs less than 2 kilograms. It consumes approximately 20 watts of power, less than that of a light bulb, as you know. But yet it defines our identity and it creates this model of the world and the reality around us. Now, also it's remarkable that, equipped with this very modest sensory perception that we have, it helps us ponder the origins of the universe and the physics of subatomic particles. So it's truly a remarkable organ that we possess. Now, it has long been a standing dream of computer scientists to build systems that compute or process information in a way the brain does. So almost 200 years back, Lady Ada Lovelace, who was an assistant to Charles Babbage, phrases in a very eloquent manner, I hope to bequeath to the generations a calculus of the nervous system. So it's like a really beautifully put, right? I mean, so people are thinking about, about the brain from, quite a while back. Now, then you also know that Alan Turing, widely regarded as the father of computer science, was fascinated by this question as to whether machines can ever think, and that led to the famous imitation game and the Turing test and so on. John von Neumann, again, one of the architects of modern computing systems, actually spent his last years writing the book titled The Computer and the Brain, which unfortunately he could not finish because of his untimely death. Now, in spite of the centuries-long interest in how the brain works. Only by the turn of the 20th century did we start getting insights into the building blocks of the brain. Due to the pioneering work of scientists such as Santiago Ramon y Cajal, we started getting a glimpse into the neural networks that help the brain process information. So Cajal made these, amazingly beautiful and detailed sketches of what he saw under the microscope, drawings that scientists and educators rely on even today. It's like truly remarkable. And in fact, Cajal was awarded the Nobel Prize in 1906 for these efforts. Now, we now know that neurons and synapses are central to how brain computes. I mean, here are shown two neurons interconnected by synapses. The dendrites, that you see here, they bring in the signals into the cell body, which is referred to as the soma. The soma aggregates this information, and if the total strength of the signal exceeds a certain threshold, then the neuron fires a signal down the axon. Now, synapses are these small, tiny gaps. The synaptic cleft is like 10 nanometers. The gap is located at the very end of the axon terminal, connecting the neuron to the other nerve cells. Now, here the neurotransmitters are used to carry the signal across the synapse to other neurons. Now, I mean, we right now know that the human brain has approximately 80 billion neurons, around 15 billion of them purely in the cerebral cortex. It has over 240 trillion synapses. And just to give you an idea, if each synapse was storing just one bit of information, that alone would amount to something like 30 terabytes. So it's around 800 books per day for 100 years, right? That's kind of the amount of synapses that we possess. The total length of the nerve fibers is approximately 150,000 kilometers, which is remarkable. And we also know that the activity in the brain is widely distributed. It is essentially a highly parallel computer, and it's remarkably efficient. By some estimates, the efficiency is around peta-ops per joule, as you can see here, right? So it's like truly, truly remarkable. It's also amazingly robust, right? Right now, when I'm speaking, I am potentially losing tens of hundreds of neurons, and it's not likely to have a major impact, at least hopefully. So this is kind of the robustness which the brain possesses. Now, our dreams of unraveling how brain computes has significant parallels to how we conquered flight, right? So we spent enormous amounts of time studying birds in flight. Then eventually we figured out that the thing to look for was this fundamental principles of aerodynamic lift arising from Bernoulli's law. And then finally, of course, we created flying machines that rival anything out there in nature. Now, the expectation is that at some point in time, we will also have an adequate theory of how brain computes. And to paraphrase Lady Lovelace, this calculus of the nervous system, right? That's what we're looking for. And then we should be able to create genuine thinking machines, which could potentially rival natural intelligence at some point. But unfortunately, brain-inspired computing seems to be way more complicated than flying, and hence it's very likely to be realized at multiple levels of abstraction, as opposed to someone coming up with this one single, theory of how brain computes. Right. So what is brain-inspired computing? So it could be many different things. As I said, it has to be realized in multiple levels of abstraction. So for example, it could be hyperdimensional computing that takes inspiration from the mere massive dimensionality of the biological neural networks. It could be oscillatory neural networks where the inspiration is drawn from the neural oscillations in the brain. That's something that people have studied and they're pretty well aware of. However, a big part of it these days is actually artificial neural networks and its variants, right? Which have gained significant prominence mostly because of this deep learning revolution that is underway. So in this tutorial, I will mostly focus on this latter part, right? Artificial neural networks and the variants of it. Now, so what are artificial neural networks? I mean, it all started in 1943 with this famous McCulloch-Pitts neuron. So Warren McCulloch, he was a neuroscientist, and Walter Pitts, I mean, he was a logician. They created this simple mathematical abstraction of a single neuron, right? So they just, represented the soma of the neuron by a node that receives logical inputs via the dendrites, which are these input signals here. It aggregates them, and based on this, a decision is made and it's output. So it's a very simple, a simplistic model that captures just the essence of what a biological neuron does. So that's all it was. Now, several years later, Frank Rosenblatt, who was another brilliant Cornell engineer, he showed that a slightly modified version of this McCulloch-Pitts neuron with synaptic weights could actually perform linear classification tasks. And that was not it. I mean, he also, one of the key inventions or innovations was that he developed a fairly simple yet relatively efficient algorithm to learn how to tune those synaptic weights to achieve that, right? So that's a famous perceptron algorithm. So that is kind of, in many ways, the first neural network to think about it, right? So you kind of can do linear classification on data using this very simple construct. Unfortunately, he tragically died in a boating accident in the age of 43. I mean, he was a very brilliant person, actually. Since then, several decades passed, and the original perceptron was quite limited in stability because it could only do linear classification, and it was trashed by much of the rest of the AI community. But in the subsequent decades, this motivated researchers to create multi-layered perceptrons by stacking them together, and then they can start doing non-linear classification tasks. And of course, one of the biggest breakthroughs was the invention of backpropagation, right? So the gradient descent and the backpropagation of errors, and that's what kind of eventually led to neural networks being a powerful thing. Of course, I mean, mostly because of the pioneering work of these three gentlemen who actually received the ACM Turing Award in 2018. So now, so that was kind of the, as you can see, the ANNs were built on top of like very simplistic abstraction of how the neural networks work. In parallel, some things were happening, right? So just a few years after the development of the McCulloch-Pitts neuron, the transistor was invented in 1947. So it was invented by Shockley, Bardeen, and Bertain, for which they received the Nobel Prize. I would argue that it is probably the single greatest invention of humankind. And soon enough, we started producing microchips with several transistors, eventually entering this so-called era of the Moore's law. I mean, this graph here shows, how we were packing transistors in microprocessors over the last 42 years. And as you can see, as in 2017, we are in the range of an astonishing 10 billion transistors per processor, right? So that's kind of the rate we are at. So we were well and truly into the Moore's law era. And Moore's law also ushered in this exponential increase in compute performance, which created several industries along the way. So if you look at in the beginning, it introduced the transistor radio, then we had the mini computers, PC, internet, mobile, and so on and so forth. So eventually, we had enough compute power and availability of data to also make neural networks work. So neural network was this niche thing sitting out there. People, it can do very limited things. People didn't really use it that much. And then suddenly there came a point where we had enough data and enough compute power that we can start doing remarkable things with neural networks. So it is indeed a sudden development. Even early 2010s, ANNs were so unpopular that they were getting dropped off the curricula in many universities. Just think about that. But the ImageNet contest in 2012 changed everything, where a deep learning based or ANN based approach outperformed all other techniques by a huge margin. So at present, as you know, deep neural networks come close to or even outperform human beings in several cognitive tasks such as image and speech recognition. Now, in the last couple of years, ANNs have established themselves to be the go-to technology for tasks such as computer vision. These are some of the latest networks out there. I mean, the most fancy ones. And also, things like for natural language processing, transformers are one type of networks that are being used there. There's this wide range of neural network architectures, all the way from feed-forward, residual, recurrent connections. So, the modern networks have hundreds of layers and hundreds of millions of synaptic weights. But the thing to note is that the fundamental building block remains the same as we had in the 1980s, right? So nothing, dramatic has happened. It's just the scale. The scale of that simple concept, is what has led to this remarkable revolution, which is the AI revolution going on. As you know, the deep neural networks or artificial neural networks are the mainstay of the AI portfolio of all the major IT companies, as you can see in some of the examples here. So in some sense, they're also heavily involved in making decisions for us, right? It's one of the things that we have to be mindful of, that they are heavily making our day-to-day decisions in many respects. Also in recent years, the applications of ANNs have exploded in areas such as healthcare, robotics, self-driving cars, also in basic science, right? And one particularly impressive demonstration was this AlphaFold, which almost solved the protein folding problem, which is like truly remarkable. The artificial neural networks have also helped us take on human beings in several strategic games, as you know. And one of the watershed moments was, of course, when AlphaGo, another deep learning or artificial neural network powered system, beat 18-time world champion Go, 18-time world Go champion Lee Sedol. He's a Korean guy, and that was a remarkable achievement. It was like a 4-1 victory in the end, and it shocked the world in many respects because no one thought that like an AI system could beat a person in a game like Go, right, which is almost beyond the reach of any computing system at that point. And ANNs have also started excelling in uniquely human abilities, such as real-time debating. This is something which IBM has been working on. It's called IBM's Project Debater, which can actually now debate pretty good world champion debaters. But still, there are some issues, right? So in spite of this success of deep learning and artificial neural networks, the key challenge remains the computational efficiency. So even though the victory of AlphaGo was truly remarkable, it was achieved at the expense of orders of magnitude higher energy consumption compared to the human opponent. So by some accounts, the AlphaGo machine employed 1,202 CPUs and 176 GPUs for this particular victory. So it didn't come cheap, right? It was a pretty expensive endeavor in the end. And today, if you look at it, it takes days, if not weeks, to train state-of-the-art deep neural networks, even with the most advanced computing hardware. The power consumption is highly undesirable and in many respects unsustainable. As you can see here, to train one of these networks, it takes 2 weeks of home energy consumption, and it's definitely not helping with climate change and some of those things which already people have pointed out, as you can see in these articles from MIT Technology Review. And in many edge and end device deep learning applications, this is even prohibitive. You cannot even afford to have this kind of energy consumption in this kind of small devices. So clearly, the computer architects have really woken up to this challenge, right? So AI and deep learning in particular is a key driver of innovation in the field. I would even argue it is probably the driver for innovation in the field, right? It has completely woken up all these people to work towards that. And part of the innovations are within the confines of conventional general purpose computing systems. For example, technologies such as storage class memory and near memory computing are being explored. You're just trying to improve your existing computing system. But the most active area of research here is right now in the space of standalone accelerators that optimize the computation and data flow to achieve very high efficiency and throughput. However, this approach is already strained, given that we are living through the waning days of Moore's law. But this is where the world is right now. So we are really focused on building these custom accelerators to somehow make it very purpose built for AI applications or deep learning applications. So another problem is that the key reason for the computational inefficiency is that you need to shuttle around these millions of synaptic weights between the processor and the memory, which remains unaddressed in any of these approaches that is being pursued. Of course, we are trying to alleviate it through many other means, but we are not fully addressing it. So another fascinating computing paradigm, which is trying to address this issue with having to move around millions of synaptic weights, is in-memory computing. So it is this non-von Neumann computing paradigm that could address this challenge that I talked about. Right. So what is in-memory computing? So in-memory computing, instead of shuttling around data between processing and memory units, as in a conventional computing architecture, we try to compute or perform the computations in place in the memory itself. Now, in that sense, there is already this uncanny resemblance to this highly entwined nature of processing and memory in the brain that we talked about earlier. Now, how is it done? It is done by exploiting in tandem the physical attributes of the memory devices, their array level organization, the peripheral circuitry, as well as the control logic. So in-memory computing as such is a broader computing paradigm with applications beyond neural networks and AI. And I would strongly encourage you to read this review article for an up-to-date survey of this field. Now, there are different types of memory technologies that could facilitate in-memory computing, and phase change memory is just one of them. I seem to have a lot of expertise on that topic. That is why I want to talk about that. And so phase change memory is based on this property of certain compounds of germanium, antimony, and tellurium, whereby they have drastically different electrical and optical properties depending on the atomic arrangement. So in the disordered amorphous phase, they have a very high resistivity, and in the ordered crystalline phase, they have very low resistivity. Now, if we sandwich this tiny volume of material between two electrodes, then we can make a memory device. And by applying suitable electrical pulses and subsequent Joule heating, this material can reversibly switch between the amorphous and crystalline phase configurations. And we can create these kind of intermediate phase configurations, which is kind of a mix of amorphous and crystalline phases. And depending on this phase configuration, the device will have different resistance values because of this change in resistivity values. And this can indeed be deciphered by biasing with a small amplitude read voltage. So it's essentially an analog storage device. And just to give you the dimensions, the diameter or the radius of such a memory device is like 10 or 20 nanometers, right? So it's really a tiny device that we're talking about. Right, so this ability to tune the conductance of these nanoscale PCM devices make them perfect candidates to emulate the synaptic elements in a neural network. So if you look at the PCM devices, when they are organized in a crossbar configuration, they can implement, for example, one layer of a neural network. So for inference, right, that is when a signal is passed through a neural network, it needs to be scaled as per the synaptic weight, right? That's a synaptic efficacy, we call it, so that they can be passed on to the next layer. And essentially, it is a matrix vector multiply operation, right? It's like a weighted, or the graded signal propagation through the network. So this can be done in order one-time complexity if you arrange these devices in a crossbar configuration. So it's like really beautiful. Now, but for training, we can actually, the synaptic weights needs to be nudged back and forth as the network sees through the examples. And this can also be exploited in a phase change memory device by exploiting the crystallization dynamics. So now I hope you get the idea of what I mean by computing in memory by exploiting the physical attributes, right? So in this case, we are performing the forward propagation or the synaptic efficacy by exploiting the Ohm's law and the Kirchhoff's current summation law. Whereas we are exploiting we are implementing the training by exploiting the crystallization dynamics of the phase change memory devices. And in both cases, we are not shuttling around the synaptic weights. So they're all fixed, like physically instantiated, right? And the signals are propagating through them. So that is the beauty of the whole thing. Now, in the case of artificial neural network inference, what we do is we train the network a priori. The synaptic weights are obtained by some training methodology, most likely in software. And then these weights are mapped to the conductance values of an array of cores, as shown here, where these are these PCM devices organized in the crossbar configuration. Each core then performs the matrix vector multiply operations corresponding to each layer, passes on those activations to the next layer, and so on and so forth. Now, so the natural question is, okay, does it work at all? And indeed it does, right? So this approach was verified experimentally using phase change memory devices that we fabricated in 90 nanometer CMOS technology. The synaptic weights are mapped onto PCM conductance values, as I mentioned earlier. There are some tricks as to how you do it, but it's not that complicated. And then you can look up for more details on this paper that we published this year. And this is a demonstration of the classification accuracy as a function of the time for this ResNet32 network on the Cipher 10 dataset. So these blue dots here. And this is a baseline accuracy that you get if you run the whole thing in a computing system, like in a standard computer. And you already see that, in spite of this analog way of computing, in spite of having all these noisy, faulty devices, your classification accuracy is comparable to the software accuracy, right? Which is like truly remarkable. And this network is actually not that easy to work with, because it's a much deeper network with very few parameters. So it was quite an achievement in some sense. So even for training, we can use a technique that we invented called mixed precision in memory computing. We can achieve software equivalent accuracies, and here is again an experimental demonstration of how a network can achieve accuracy, software equivalent accuracy by training. So essentially, what we do is we start with a random distribution of phase change memory conductance values, and then they are kind of nudged back and forth by exploiting the crystallization dynamics of the memory devices, right? And then eventually they reach these optimal synaptic values. And once they reach, so this is a training process. So this, you can see the accuracy rising, as you have many more training epochs. And once you reach that classification accuracy, in this case is a test accuracy here, and then you can stop your training process. You stop nudging them back and forth, and then you can perform inference on that. So you can say that it can perform inferences if forever, in fact, right? So that's the beauty of the whole thing. Now, so in fact, this hardware on which we did this demonstration is actually available on the cloud for public access. So it's possible to go to this link and try out, inferring on this chip that was trained this particular manner, entirely on hardware. And I would strongly encourage everyone to try this out if possible. I would also appreciate if you could help with this simulator, which we open sourced end of last year to establish some of these algorithms, right? Like the software equivalent training and inference of deep neural networks using in-memory computing. I think it'll be really cool if you could take a look at this link here and also contribute to this project. Now, so one of the questions which many of you might be interested, particularly in this audience, is there a photonic counterpart to in-memory computing? So a few years back, a photonic memory device was proposed based on phase change materials again. So a phase change memory segment is fabricated on top of a nanophotonic waveguide. Now, information is now stored again in terms of the phase configuration of this segment, just like the electronic counterpart. Both reading and writing are now performed via ultra-short optical pulses. Now, during write, we exploit the evanescent coupling and the subsequent heating to alter the phase configuration. And as you know, the phase configuration in turn affects the optical absorption. So information can now be deciphered by monitoring the optical transmission when a lower energy optical read pulses are applied. So that's kind of the idea. So it's almost a direct analog of the electrical phase change memory that I talked about. Now, so folks in Oxford and Münster have shown that these devices can store a continuum of transmit levels, right? And by clever choice of device geometry and pulse shapes and so on, I mean, they can obtain these very nice programming curves, so to speak. Again, very similar to the kind of curves that I showed for the electronic phase change memory. Now, but what more can we do with this? We can actually perform now photonic in-memory computing, right? Or the synaptic efficacy that I talked about earlier, the grading of inputs. For example, if you have two operands like alpha and C, which you want to multiply and get a beta, then you can store one of these operands in terms of the transmitted state. The other one can be mapped to the input read power. Then the output read power will be proportional to the result. So that is very similar again to how we did the whole operation using Ohm's law in electronic in-memory computing. So as Anne-Catherine also alluded to in the beginning, so we recently extended this work to implement a photonic processor that can implement now multiple matrix vector multiply operations at the same time. So it's just an extension of that concept that I talked about earlier. Now, as you know, one of the biggest advances of photonics or electronics is this ability to do wavelength diffusion multiplexing. And one application that is particularly amenable to this is convolution. So this is just an illustration of how convolution, a 2D convolution works. Now, there is a fixed convolution kernel, right, which is kind of multiplied, or it's scanned over the image, right? So that's what you do. So if you look at it, it is a whole bunch of matrix vector multiplications. That's what that you need to do at the same time. So what we did is the fixed convolution kernels are mapped onto the photonic memory states that I talked about earlier. So this is kind of the photonic crossbar array, again, equivalent to the crossbar array that I talked about in the electronic domain. And this one now stores the convolution kernel, right? The nice thing is that convolution kernels are rather small, even for state-of-the-art deep neural networks. So you can easily have a crossbar array of photonic memory elements storing them. But now the input vectors corresponding to the image data, right? They are now encoded on multiple wavelengths derived from an optical frequency comb. So each of these wavelengths will now encode one of the inputs that you're looking for. Now, this will allow us to perform all these matrix vector multiply operations associated with a single convolution operation in a single time step. So this is like really remarkable. And so essentially we are performing the whole convolution in one single time step, right? So this is beyond the reach of any electronic processor that I'm aware of. And it's definitely, it has a huge potential to reduce the latency involved in artificial neural network inference by orders of magnitude. So it's a classic example of photonic in-memory computing as applied in artificial neural networks. Now, so I want to, as I said, I just want to spend a bit more time on some of the algorithmic challenges out there and the work going on in that space. So let's just look at this concept of neurosymbolic AI, right? So if you look at a state-of-the-art deep neural network, and if you show this image to that, there's a good chance that it will recognize that as a teddy bear. And in fact, this is indeed an exhibit in the Museum of Modern Art in New York, and this is definitely not a teddy bear, right? So what you see is that these kind of networks, they fall apart when they encounter images in unusual contexts. So there's another example where there is if an object such as a guitar is now superimposed on this image from the jungle, then it is recognized as a bird, presumably because it is colorful, right? And it's in the jungle. Funny enough, the monkey suddenly becomes a person because maybe it's close to a guitar. So it's kind of strange, right? So ANNs, in some sense, are excellent function approximators, and they are very good at it, but they don't have a real understanding, it appears. So again, there's another illustration of these kind of there are very sophisticated captioning systems right now based on neural networks. So you show them an image and tell you what it is, and usually they do a pretty good job, right? And it's being widely used. But then you can show these kind of images, such as this one here, and says a man riding a motorcycle on a bike on a beach, an airplane parked on the tarmac at an airport, a group of people standing on top of a beach. So, it's kind of weird, right? I mean, they don't have a fundamental understanding of these images. So they just, as I said earlier, they are like glorified function approximators in some sense. So this is a huge problem. It's likely that combining artificial neural networks with symbolic AI could address some of the challenges mentioned earlier. So symbolic AI was another form of AI that has been around since the inception of artificial intelligence AI in the 1950s. In some sense, symbolic AI is likely to gain a resurgence because of the success of artificial neural networks. So there is a significant research area within IBM, in particular, the MIT IBM Watson AI lab, to kind of look at this problem. So I just want to point out some of the severe shortcomings of artificial neural networks and how people are trying to address it through different algorithmic means. Now, another fascinating area of research is memory augmented neural networks. So in this domain, one of the huge challenges for artificial neural networks is learning from few examples, right? So we do not learn how a dog looks by looking at a million images of different types of dogs, right? So that is not the way we learn it. However, recent research has shown that by having access to an explicit memory can significantly improve the ability to learn from few examples. So this is a so-called few-shot learning problem, which we are all very good at. Now, note that an artificial neural network has itself an implicit memory. So here we are talking about a separate memory that the neural network can read from and write into, right? That's the whole idea of neural networks with explicit memory or memory augmented neural networks, as they are sometimes called. And this representation of knowledge in the form of an explicit memory could also help with more complex tasks such as reasoning, planning, question answering, and so on. So that is gaining a lot of traction these days. So in a very recent work that we did, we found a way to realize the explicit memory in terms of high dimensional vectors, binary vectors of very high dimension. So we attached a neural network to a so-called HD, a bunch of HD vectors, high dimensional vectors. So this merger of neural networks with high dimensional computing could pave the way for robust vector symbolic manipulations and so on. Now, it could also facilitate robust manipulations using in-memory computing, something we already had demonstrated recently for high-dimensional computing in a Nature Electronics paper, which actually appeared on the cover, actually. So again, I just want to give you a glimpse of where the field is going, right? So we are right now trying to attach neural networks to symbolic logic. We are trying to attach neural networks to explicit memory so that you can condense your kind of knowledge in that explicit memory, and so on and so forth. And in this work, we were trying to actually combine that explicit memory with this very fascinating area of hyperdimensional computing and vector symbolic architectures. Now, in the last part, I want to talk about more biologically plausible ANNs, right? So there's another very interesting application domain. So if you look at this conventional artificial neural networks, neurons are static nonlinear functions right from the time of the McCulloch-Pitts neuron that we described. Synapses are scalar multiply units, and information is transmitted as floating point numbers. But we all know that in biological neural networks, neurons and synapses are dynamic entities, right? Information is encoded in time and transmitted in terms of spikes. And these so-called spiking neural networks are asynchronous. They don't have a global clock, and they are event-driven, right? They only compute when you have an event. They're triggered by an event. So these are some of the fundamental differences between biological neural networks and the current artificial neural networks. So the natural question is, okay, then what is SNN bringing, right? So is there any potential benefit of having this additional machinery attached to the artificial neural networks? So due to the event-driven nature of spiking neural networks, there could be significant energy efficiency. We do not have to maintain a global clock, and we only compute when triggered by data. So this could definitely bring in some energy efficiency. That could be one advantage. Now, the temporal encoding of information could lead to ultra-low latency. The spikes could propagate across layers of neurons, unlike conventional neural networks where we process layer by layer. So it's a very nice depiction of that. It was something which I got from Professor Simon Thorpe, where you can actually see how fast your brain can respond to visual stimuli just because spikes can just propagate through the layers without having to wait for the full layer to be computed. So it's like really an amazing potential for spiking neural networks. Compared to the very expensive backprop-based learning in artificial neural networks, local event-based learning, which most likely the brain is doing, right? I don't think we are doing backpropagation in the brain. So it could be highly efficient, right? So this is another big advantage that could come. And finally, because of this additional synaptic dynamics, this could bestow spiking neural networks with computational superiority in certain tasks, right? Because your synapses are not just scalar multiply units, but they have their own dynamics. So that should definitely bring in some computational benefit. In fact, this is what we recently showed again in this archive paper, where we showed that if you have spiking neural networks and if you equip them with a so-called short-term spike timing dependent plasticity, I again don't want to go to details of it, but you can look up this paper. You can actually infer very well in dynamically changing environments. It's actually a very difficult task for conventional neural networks. So they're very great at recognizing handwritten digits, for example, like this. But if they are now being occluded with things like that, then the classification accuracy drops significantly. But we showed that spiking neural networks with this short-term spike timing dependent plasticity can deal with this remarkably well and could outperform many different types of conventional neural networks. Again, I would encourage you to go and look up this paper for more details. But again, I just want to give a flavor of where the research is going in the algorithmic front. Right, so I just want to, as I said earlier, so my idea was just to give a glimpse of what is going on in those three domains, right? Now, so the AI revolution is likely to shape our society and economics in profound ways in the coming years and decades. And this revolution was fueled largely by artificial neural networks, which in turn was inspired by how brain computes. So the AI revolution is also likely to dramatically change the landscape of our computing systems as we transition away from the semiconductor scaling laws. So one natural question is, okay, where do we stand compared to natural intelligence? So a few years back, IBM created this very nice taxonomy of artificial intelligence. So narrow AI, where AI systems perform exceedingly well in a single task in a single domain. Then there is broad AI, where a system can excel in multiple tasks across multiple domains. And it should also be able to reason and explain and learn from fewer examples. And I believe that this is probably the current frontier of AI as we talk about it, right? It's the broad AI we are talking about. And down the road comes general AI that comes closer to the true fluid intelligence that our brain possesses and the common sense that I talked about briefly. But we are potentially still decades away. I don't think we still haven't figured out that calculus of the nervous system, right? To really understand what is going on there. But in parallel, I also see a lot of developments going on in the hardware domain with, that could be fueling the algorithmic advances as we go along. Right now, it is the age of CPUs, GPUs, and digital application-specific ICs. But soon enough, I think we should start seeing non-von Neumann architecture accelerators, such as in-memory computing-based architectures that I mentioned about earlier. So with that, I would like to summarize. So brain is this remarkably unique supercomputer that each one of us possesses. And an adequate theory of how brain computes is still lacking. Artificial neural networks, loosely inspired by how brain computes, along with advances in semiconductor technology and information technology, is what is ushered in this AI revolution that we are living through. Now, to address this energy efficiency problem, new forms of computing, such as in-memory computing, are being explored. And I showed that using electronic phase change memory devices and in-memory computing, we can achieve ISO accuracy and inference and training. And photonic in-memory computing could be very interesting in applications where you need very good, very small latency. There's also significant extensions to traditional artificial neural networks being proposed and researched. I just mentioned 3 of them. So one of them is neurosymbolic AI, where you combine neural networks with symbolic reasoning. Then I talked briefly about neural networks with explicit memory. I think that's also a very fascinating research area. And then finally, more biologically plausible artificial neural networks, which could bring in their own unique benefits while addressing some of the challenges in this domain. So with that, but I just want to point out that we are still at the very early days of brain-inspired computing. So there is still a way to go before we can start solving problems like fluid intelligence and and common sense and humor and so on. So I think we are still in the early days, but I'm really happy about the way both the algorithmic and technology and the device, all those communities are coming together to make this happen. And I really hope to see a lot of advances in the coming years. So with that, I would like to conclude, and I'll be glad to take questions.
Yeah, Abu, thank you very, very much for this wonderful presentation. I think you did an amazing job, especially when it comes to showing the depth of your research, but also just how broad it goes. I think the interest can be seen from all the questions that were asked during your talk. And I would just like to read some of them out loud and would like to give you the word then to say some comments on that. So one of our attendees was asking that you mentioned in the beginning that the brain uses very little power. And this is like one of the motivations for going towards photonic solutions. But where does it come from? Is that, so the attendant asked, do neurons work electronically, and is it an issue of ohmic losses, or is it just like not clear where this huge energy difference comes from?
Right. I think part of it comes from the fact that we have this end-to-end memory and processing, right? That's also why I was very much interested in in-memory computing, right? So it doesn't. I mean, if you have like 240 trillion synapses, it doesn't make any sense to move them around when you're performing computation, right? They have to be stay put. So that could be one aspect, right? I mean, why brain is very efficient. But on the other hand, there could also be a lot of algorithmic aspects. For example, we still don't have a good understanding as to how training happens in the brain, right? So, definitely it's not backpropagation and gradient descent. I mean, there could be some, people have postulated some ways in which the brain could be doing some of those things, but it's very unlikely that it'll be anything like how we do it in our computer, right? Because we all know how as I showed you some of the numbers, it takes 2 weeks of our home consumption to train a large network. So it's very unlikely that brain is doing something like that. So there are some local event-based learning most likely it is doing, which we don't fully understand, right? So from a training perspective, I think some of the efficiency could just be coming from the algorithmic side. But I think the in-memory computing is a big aspect too, because if you're not moving data, I think you can be fairly efficient.
Thank you very much. Then again, everyone is really excited about your talk, and thanks you for the great presentation. But there's also the question of, can you maintain the states of the phase scheme you showed for the phase change related in-memory computing? So the question was here, is the phase stable for a long period of time? Or do you have to bring in energy again?
Yeah, so I think the phase configuration, right? Is fairly stable. As you know very well too, right? And Catherine, but the challenge, of course, is resistance drift, right? So this is one of the things where phase change has this very quirky behavior, whereby you create like a amorphous phase change material, and then it keeps on wanting to go to an ideal glass state, right? So it starts drifting towards that ideal glass state. So this is what we typically refer to as drift in PCM. So it's really not a phase transition. It's not like amorphous is going towards crystalline. It's really amorphous is going towards a happier amorphous phase, right? Or a less energetically energetic state. So this is kind of the challenge that we have. And maybe you already noticed here in one of the, maybe I can quickly go there if it's quick enough. Like in this task, for example, you see this yellow line here, right? You see that the classification accuracy is very good in the beginning, and then you start dropping in accuracy. And this is precisely because of this resistance drift, because your conductance is drifting away in time. Fortunately, this is something that we can deal with quite easily with a very simple circuitry. So that is why you can lift it up to the blue line here without much hassle. But this is indeed a pain, right? Because you really have to do something in addition to that. So this would be one thing that I would really like to avoid. The other thing is, of course, there is a lot of noise in the system. But here again, at least for deep learning inference, you don't need very high precision. And definitely the synapses in the brain are not like floating point units, right? So I think this is again one place where I think maybe we are fine there. But yeah, some deterministic effects like resistance drift could be a problem, and we need to kind of, there should be some research from the material side to deal with that. And also from the device side. Yeah.
And is it an issue that if you want to go, if you want to switch between the states, that thermalization needs to happen in the lattice, and that this just has like a time limit on how fast you can go, or is this irrelevant?
Not really, at least for the electronic phase change materials, right? Because these are really tiny, and usually your thermal time constants are like 5 nanoseconds or so. So if your pulses have a trailing edge of more than 5 nanoseconds, you're already beyond the thermal time constants. So yeah, that's not a huge problem, at least for electronic phase change memory.
And do you think for brain-inspired computing that also you mentioned your great overview on memory devices and applications for in-memory computing, and you only mentioned that phase change materials are one option, but also many people are working on magnetic materials. So do you see they can both be worked on at the same time, or would that be at some point one of the concept wins the race towards technological realization?
Yeah, I think there could be. I believe there are, there is option for many different candidates. Definitely, phase change memory and resistive RAM are particularly suitable because they have this wide conductance window, which magnetic storage devices don't have, right? And they have a very, very small resistance margin. So it's possible that resistive RAM and PCM are better suited for the type of in-memory computing that I'm talking about here. But on the other hand, phase change memory is also commercialized, right? So there's a commercial product out there, and people are making dies with 128 gigabits, right? So this is definitely an advantage for phase change memory. People know their physics much better. So I have more hope in phase change memory, but for sure, I think resistive RAM is also a very good candidate. I mean, spintronic devices could also play a role there, but in a different way, right? They could probably implement like logical operations or something, but it's a little bit difficult to see how they can have an analog conductance value across a large array because of the small resistance windows that they have. And also the resistance value themselves are very small, which is not particularly nice when you want to make a large crossbar array.
Thank you. Then we have a question from the audience. Where do you see the disadvantages of photonic neural networks in the comparison to the electric version?
Yeah, I think the photonic neural networks, the photonic processor is extremely nice, right? But my fear is that when you start hooking them together, you start losing some of the advantages. So it's like having a Ferrari, and then I don't know, it is like kind of made to run on a on a small tiny street, right? So you kind of have this beautiful processor, then you now need to implement some nonlinear functions. You need to do something else, and you may have to convert into the electrical domain for whatever reason. Then you start losing what you gained, right? I mean, there are, of course, people have worked out some ways to do certain things all using light and without having too many, these kind of bottlenecks. But I'm really afraid of that, especially when we try to scale it towards very large networks, right? I mean, and for small networks, I think it should be fine. We may have some solution there. But if you really want to scale it up, then I think we have to worry about some of these in-between things. Again, I mean, just to illustrate what I'm talking about here, you just look at this chip, right? I mean, you have these crossbars, but then you have these digital, units here, control units here. There are things beyond just the array, right? So we have to worry about that too. And we may have to implement some of them also using light.
There's also a very detailed question on what is the upper bound of n kernels for the frequency comp demonstration. So meaning also we're implying what is the largest resolution of a photo in a that you can imagine with this demonstration?
I have to recollect what it was. I mean, we had a frequency gap of 100 gigahertz. But I have to now go back and check how small we can go, because this, as you know, these comps are from EPFL, and Tobias is an expert on that, right? So yeah, I don't think I would be able to answer that.
And for your convolutional neural network, how are you applying these nonlinear operators?
No, so I mean, I see. The good thing is that for these simple networks, you can have something like ReLU, right? Which is a very simple nonlinear operator. So it just means that you just kick off the negative signal, right? So you just make them 0. So these kind of things are fairly easy to implement. That's why I meant to say that, if you have very simple neural networks, then you can get away with some of these problems. But when you want to implement like a much larger neural network, then you are faced with the challenges of having to implement more sophisticated nonlinear functions and so on.
They're also a bit more towards your outlook. So can you, first of all, there was a question. What do you think would be the next problem really to solve for neural networks? So examples where you're like folding proteins, image recognition, or you mentioned all these play and go. So where do you think would be a nice way to show what is possible?
Right. So I think my own take on that is, I I mean, neural networks, I mean, have established themselves as very good function approximators, right? I mean, that's what they're good at. So right now, looks like we are right now taking that good function approximator, and then we are combining it with other stuff to do good, cool stuff, right? So if you look at the protein folding or the Go even, you kind of combine neural networks with very good, search algorithms like Monte Carlo tree search, right? And then try to do something based on that. Then, what we're doing in MIT IBM lab is combining neural networks with symbolic AI and try to bring in reasoning into the picture, right? Because neural networks are great at identifying the objects, but then you still need to marry it with reasoning. Memory augmented neural networks, right? It will be very nice if neural networks have access to external memory, right? And not just the implicit memory that the neural network has. And there's even evidence from the brain that there could be potentially some architectures like that we could conjure up in the brain. So yeah, I mean, these are all, I mean, I see it like, people are now trying to combine neural networks with many other schemes to do better things, correct? So that's where the field is. My main concern is the lack of common sense, right? So that's the part I think which we still haven't figured out, and we are still struggling to solve, which is common sense, right? Which is like something so simple for us. I mean, we don't even have a good idea how to approach that.
So do you think there's also still a lack of insight in biology or neurobiology, that you can really can't really say what you actually have to build to make the same functionality in a way?
Yes, absolutely. As I said, I think the only thing that right now we are good at is we have found out that neural networks, when they scale up, they can approximate things very well, right? They're very glorified function approximators. They're excellent at doing that. But I don't think we are closer to understanding intelligence or fluid intelligence or common sense yet, right? I mean, it could be that neural networks combined with some of these other techniques may get us closer there, but I think we are still lacking a lot in that domain. Like, how do you reason, right? I mean, these kind of things, which is what is really troublesome.
Yeah, I think it's fascinating how this again brings like physics in a way, and then again philosophy also a bit together.
Exactly.
So it's really like a
and psychology,
broad topic.
Right? Yeah. No, and what's also new, as I said, is that now a lot of people from different backgrounds are tuning in. I mean, I myself am not coming from neuroscience background, but then we are all trying to tune in, right, and try to understand what is going on. And it seems like a more concerted effort these days, with everyone joining in the effort, which is really amazing.
Yeah, so I think also your topic and your talk resonated with many and showed that many were so interested, and we're also very glad that many on YouTube are watching and also here. So I thank you very much for your presentation, and we'll all follow your publications and off the field, and we're excited to hear what's going on in the next couple of years. So thank you very much, Abu, for your time.
Thank you. Thanks a lot.